Okay, let's talk about the explanation of what does it mean to be solving for a trigonometric double angle here. And when we're doing this, what I want you to understand is that this all comes back to that I'm still taking the sine or the cosine of some specific theta. And what this x is just in place for is what angle am I giving you that I'm up here. This is just like the same idea where if you had 2x in algebra, it's 2 times x. So what angle am I multiplying by 2 that gives me a ratio of 1/2? So I'm going to talk about this over here in this idea of on the quadrantal plane here. So let's take a look at 60 degrees. So if I take a look here and I say this is 60 degrees. Well, I need to talk about this in the sense of coterminals because every angle that ends on this 60 degrees will also have the same trigonometric ratio that 60 degrees has. So it doesn't matter if it's positive or it's negative, but what's going to matter here is in the original problem, where is your interval? Does your interval allow those negative angles? Will allow those positive angles? So all of the coterminals that deal with 60 degrees. So 60 degrees could be another coterminal could be 420 degrees. You could also look at it in the negative sense, where the negative sense could be negative 300 degrees. And I can keep going and going and going and going, but the point is here is that this all needs to be in reference to coming back and having a coterminal in this 60 degrees. So here's the thing with that. When I start talking about doubling angles, well then there are other ways that I can come up with 60 as opposed to just coming up with saying that it is 420, because if you look at 420 by itself and I'm not doing anything to it, then that 420 is on an interval between 0 and 4 or 0 and 720, or you could say it's on the interval of 360 to 720 or whatever, whichever interval you describe there. So the important thing here is that whatever your interval limits you to is what you have to stay constrained within. And when we're talking about a double angle, what I mean by that is well, how did I make 60 degrees if I'm doing a doubling some angle? Well, if I come up here and I look at this, well, 60 degrees cut in half is 30 degrees. Well, 30 degrees also, what you notice here is that if I double 30, it would give me that 60. So I'm trying to find the specific angle that I'm going to double that will give me this 60, that will allow me to give me a specific ratio that or a specific answer that I want. And also what you need to look at is now you need to look at all the coterminals as well, and that's the important part here. So if I look at the coterminal of 420, well, what angle did I double to make 420? And the angle that I doubled to make 420, you'll find, was 210 degrees. So if I draw that angle in, so that angle from here to here is 210. And what you should take note of here is something very important and special occurs here. That when I doubled, when I took half of this coterminal, what I want you to note is that actually that 210 degrees created a vertical angle here with the 30 degrees, because this, between 180 and 210, is actually also 30 degrees. And what that creates here, since it's a vertical angle, you must note that this right here is a straight line. So because that's a straight line, that's very, very important. So essentially what I've done here is that I've taken this 30 degrees, and if I add 180 to it, you'll find that I also get 210. And that occurs for a very specific reason, because we're talking about double angles. Because there is some theta between 0 and 360 that exists, that if I doubled it, it would give me 360, but it would not give me any more than the full circle. And when you find that out, that theta is equal to 180 degrees. So every single angle, okay, that I'm talking about from the first quadrant, okay, I can add 180 degrees to it, and it won't give me anything greater than 360. Also, you'll find from the second quadrant, I can do that. I can add 180 degrees to it, and it will give me something that's not over a full circle. But once I go into this third and fourth quadrant, then those things change. But all of the trigonometric ratios, when we solve them, always give you their answer in the first quadrant. So that's an important another thing to note. So basically what I'm talking about here is that to solve these problems, what you need to look at is what angle in the first quadrant are you doubling to create your new angle, and then use that angle, that new reference angle that you found that was doubled, to add 180 to it to find your other your other angle that you can double on the interval of 0 to 360. That gives you a reference angle here. So that's just for 60. And please, what I note here is when I said that you can't double an angle in the third or the fourth, you can double those angles. We're just not going to get 60 from it. So what I wanted to point out to you is that for 60 degrees, the only ones that you can double are 30 and 210. So what we're now going to talk about here, okay, is if I come up to this, is that I've got a sine of 2x, and now I'm going to relate this back to this problem. So if I take a look at the sine of just some angle, so forget that I'm doubling an angle, and let's just say I have the sine of some angle, and that ratio is 1/2. Well, what did that angle have to be that's going to give me 1/2? And the reason I'm looking at it that way is because if I know what that angle is that gives me the 1/2, then I can just cut it in half, and that will tell me what the double angle is. So the x that must give me 1/2. Remember, now my interval is 0 to 2 pi, so I'm not going to be working with degrees. Okay, it's just easy. I think it's a little bit easier to explain that way. It's easier to see. But now I'm working with the radian measure here, and so I'm going to explain it with degrees, and then tell you what the degree measure is, and then just tell you what it is in radians. So the sine of 1/2 is 30 degrees. So 30 degrees in radians is pi over 3. Or pi over 6, I'm sorry, pi over 6. So if this is pi over 6, that's important. Now I also have to remember that sine is not just positive in the first quadrant. Sine is also positive in another quadrant. And sine is positive in the second quadrant. And now I'm going to use this reference angle to say, okay, well it's also positive at 5 pi over 6. So now I'm going to take this. So this is just my kind of my work and the set me up. So what angle am I doubling to get pi over 6 so that when I take the sine of it, of sine times 2 times some angle, that it gives me pi over 6 so that I can say that that is 1/2. And the way that you do that is you just simply would say that 2x has to be pi over 6, and it also had to be that 5 pi over 6. So therefore, the angle that you're doubling, okay, I would just multiply this by 1/2 because I would divide the x by 2, so it just goes back to algebra 1, divide by 2, it's not like I'm trying to trick you here. Divide by 2 and divide everything here by 2, which is really multiplying by 1/2. So I get pi over 6 times 1/2 is pi over 12, and 5 pi over 6 times 1/2 is 5 pi over 12. And the important thing to note here is that yes, that is going to be, if I double it, it will be 5 pi over 6. Because if I double 5, it gives me 10. Well, 10 over 12 is actually 5 over 6 because 2 goes into 10 and 12. So now I'm going to apply that new idea. Well, this is the angle that I cut in half, okay, that gives me this pi over 6. So remember how you went back to this, and I was showing you that phenomenon that occurred, that vertical angle actually was just enabling me to add 180 degrees. So in this case, this now, my pi over 12, is that angle that I'm cutting in half, so I can use its vertical angle so I can find the other one. So if I take pi over 12 and I add pi to it, which is 180 degrees in radians, I'm going to get that this is 13 pi over 12. And if I take 5 pi over 12, so remember I now have to do it for all the angles that I've cut in half. So 5 pi over 12, and if I take that and I add pi to that, I'm going to get 17 pi over 12. And now the important thing here is I just want to show you that yes, this is true, and that yes, that these are working. But the other thing I want you to note is that my interval says from 0 to 2 pi. So if I went to this 13 pi over 12 and I added another pi to that, another pi to that would give me 25 pi over 12. And 25 pi over 12 is not good because 25 pi over 12 is 2 and 1/12 pi, and that is no longer on the interval of 0 to 2 pi. So I would keep going until I found out that it doesn't land in my interval anymore. So I would just keep adding those values. And because you're adding 180, that's why I'm only having to do it one time. But if I was adding a smaller number, I might have to do it a couple of times. So this pi over 12, 5 pi over 12, 13 pi over 12, 17 pi over 12. So let's just prove very quickly that if I doubled 13 pi over 12, that it is actually going to give me the coterminal of pi over 6. So here we go. So this becomes 26 pi over 12. So I'm just multiplying fractions here. And 26 pi over 12, well, that's the same thing, really, as if I took 2 pi out, which is 24 over 12, which is 2 pi, and added to it 2 pi over 12. Well, 2 pi over 12, guess what? That is pi over 6. So that 2 pi plus that little bit extra of an angle of pi over 6 ends up giving me the coterminal, and that's what I was looking for. So I hope you understand, and that helps with what you're trying to do for solving for double angles.